Welcome to This Explainer. Today, we're going to systematically break down the core pillars of machine learning. Think of this as a high-speed masterclass. So if you've been looking to consolidate your understanding of the entire stack, I'm talking from the foundational math all the way up to advanced ensemble theory, well, you are in exactly the right place. Let's get right into it.
Okay, here is our syllabus for today. Section 1, what is machine learning? Section 2, data splits and leakage. Section 3, overfitting and underfitting. Section 4, evaluation metrics. Section 5, loss and optimization. And finally, Section 6, the power of ensembles.
All right, Section 1. What is machine learning? The learning problem.
We've got to begin at the absolute foundation, right? So what actually is a machine learning model in plain English? Honestly, it's way simpler than all the industry jargon makes it sound. The crucial point here is that a model, whether it's just a simple straight line used to predict house prices or a massive vision transformer like a plant Pokédex with 86 million knobs, is really just a machine that we tune until its answers match reality. That's it. You feed data in, you get an answer out. And training? Well, training is just the mechanical search for the specific knob settings that make your wrongness score, what we call your loss function, as small as possible. Now, this brilliantly illustrates the two primary types of supervised learning, the kind where you actually have an answer sheet. Your choice here is absolutely crucial because it determines your entire loss function and your success metrics. If your model outputs a category, like, say, the DeepGuard system classifying audio as real or fake, that is classification. But if it outputs a number on a continuous scale, like the Dragonstock project forecasting next week's unit demand, that's regression. It's super important to get this right. Get this choice wrong, and you're basically measuring your model with the wrong ruler.
Moving right along to Section 2, data splits and validation, hiding the answer key. So why in the world would you deliberately hide data from your own model? Well, because a model that only performs well on the exact examples it trained on is absolutely useless to us. To fix this, you split your data. The model learns on the training set, it makes its development decisions on the validation set, and then, and this is key, it touches the test set strictly once as a final, honest exam. Think of the validation set like a mock exam, right? The marks don't go on your final certificate, but they tell you exactly what you need to revise. The instant you look at your test score and tweak a parameter based on it, bam. Your test set secretly becomes a validation set, and that score is utterly compromised. Okay, now we need to talk about the silent killer of impressive results. Data leakage. This happens when information sneaks into your training data that just wouldn't be there in the real world. For example, if you normalize your whole dataset before splitting it, the test data statistics have secretly bled into the training process. Not good. Or think about audio detection systems like DeepGuard. If clips from the exact same speaker end up in both the training and test sets, your model might just be learning to recognize that specific voice rather than actually detecting synthetic audio artifacts. Leakage is literally the reason why a perfect 0.99 development score so often turns into total garbage in production. But wait, what if your dataset is really tiny? Well, for small datasets, k-fold cross-validation is just a brilliant statistical technique. It essentially buys you a robust evaluation by using a bit of extra computational compute. Here's how it works. Every single data point gets to be used for validation exactly once because we swap the chunks around for each training round. You're basically trading hardware time for statistical certainty, which is a pretty great deal. Okay, Section 3, overfitting and underfitting, bias versus variance. So, let's see what actually happens when learning goes wrong. If training is a search, how do we know if we're heading in the right direction? Well, overfitting is kind of like a student who memorized last year's test but completely freezes on new questions. We call this high variance. You can spot it clearly on a learning curve. The training loss keeps dropping, but the validation loss bottoms out and starts rising again. It's a literal fork in the road. On the flip side, underfitting, or high bias, is the student who just didn't study at all. This gives you terrible scores across the board because the model is just too simple to capture the pattern. So what do you do when your model overfits? You pull out these tools to either add data constraints or take away some of the model's freedom. L1 regularization, for instance, acts like a ruthless editor. It drives small weights to exactly 0, which gives you a sparse model. L2, on the other hand, just shrinks them smoothly. Now, in deep learning, dropout is super fascinating. By randomly turning off neurons during training, it literally prevents them from co-adapting. This forces each part of the network to learn robust, independent features. And finally, early stopping. It does exactly what it says on the tin. It simply halts training the very moment your validation loss hits that fork we talked about and starts rising. Moving to Section 4, Essential evaluation metrics, beyond accuracy.
So how do we actually measure success beyond just basic accuracy? Well, the confusion matrix is the source of everything. Let's think about a banking deployment for a second. A false negative? That lets a scammer's voice clone right into an account. No way do you want that. But a false positive? That locks a legitimate, frustrated customer out of their own money. Every single business decision is a trade-off between these two specific errors, and your operating threshold is what determines exactly where you sit on that sliding scale.
And listen, 99% accuracy means absolutely nothing if your data is severely imbalanced. Like, say, if 99% of transactions are legitimate anyway. That's why we use the F1 score. Since it's the harmonic mean of precision and recall, it aggressively drags the final score down toward the lower number. It literally forces your model to be good at both catching the fraud and avoiding the false alarms. You simply cannot game the F1 score by just blindly guessing the majority class.
Now, let's see how this builds for regression tasks, like our Dragon stock demand forecasting. You have to choose your penalty style here. You choose mean absolute error, or MAE, for an honest, proportional average of your mistakes. But you choose root mean squared error, or RMSE, if rare, massive errors would destroy your business. Let's say a massive stock out on your busiest weekend costs you everything. If that's the case, you want a metric like RMSE that squares the big misses to punish the model appropriately.
All right, on to Section 5, Loss and Optimization, the search for the low point.
We've got the data, we've got the metrics, but how does the machine actually mechanically search for the right knob settings? Well, imagine a hiker in thick fog, just feeling the slope under their feet to try and find the valley floor. That is gradient descent in a nutshell. You can't see the whole landscape, so you just compute the local gradient and take a step downhill. And we do this in mini batches. Hardware absolutely loves the matrix math of mini batches. It saturates the GPU while adding just enough statistical noise to shake the model out of any shallow local minimums. Oh, and if you want a sensible default optimizer, you use Addo. It gives every single parameter its own adaptive learning rate based on momentum. Now, you might be wondering, how on earth do we find that slope for 86 million parameters all at once? The answer is backpropagation. This backwards pass is the absolute genius of deep learning efficiency. By applying the calculus chain rule backward from the final error, you can calculate exactly how much every single weight contributed to the mistake, and you're reusing your mathematical operations as you go. It's incredible. It lets you adjust millions of parameters in one go without having to rerun the network for every single knob.
And finally, Section 6, the power of ensembles, the wisdom of the crowd. Combining multiple models is really what separates the novices from the master architects. There are two major philosophies here. First, bagging. Think random forests. Bagging averages away individual noise by training models independently in parallel on resample data. It primarily attacks high variance. Boosting, on the other hand, trains models sequentially. Each new, weak tree is specifically fitted to correct the residual errors, the gradient, of the trees that came right before it. So while bagging targets variance, boosting systematically attacks high bias. And this leads us to a pretty fascinating Nubistry reality. Look, deep learning is amazing, but it's really meant for perceptual data like audio or images, where features have to be learned from scratch. But for structured tabular datasets, XGBoost remains the undisputed champion. It builds on gradient boosting by adding built-in regularization and shrinkage. It trains in a fraction of the time, and crucially, this is huge, you can actually show the feature importance to a client and have them understand it. At the end of the day, you have to pick the tool based on the shape of the data. So the core takeaway you need to memorize here is that ensembles only work if the models make independent, decorrelated mistakes. Think about it. If 1,000 models all copy the exact same wrong answer, your entire ensemble fails. You have to manufacture that decorrelation yourself, whether that's through feeding them different subsamples of data or restricting the features they're even allowed to look at. When their noise is truly independent, the mistakes cancel out in the average, and the true signal shines through perfectly. Thank you so much for joining this Masterclass Explainer today. As we wrap up, I want to leave you with one final thought. We spend all this time building complex hardware, intricate data pipelines, and super sophisticated mathematics, but it all comes down to generalization. If a model just memorizes last year's answers, can you truly say it has learned anything at all? Take these frameworks into your next technical build. Scrutinize your metrics, guard your test sets fiercely, and make sure your model actually understands the real world rather than just memorizing it. See you next time.